Is it going to be you and me?
I think Umar, he will join. Yeah, he just joined now. Hello, Umar.
Hi, Ali. Hi, Professor Sevgi. Hello, everyone. Hello, everyone. This evening we have a very interesting guest speaker, an IEEE fellow and an APS distinguished lecturer, Professor Levent Sevgi, who focus on not only the academic research part but also the teaching part of the electromagnetics field. So it will be very interesting to listen this lecture, and I am really excited to see such a lecture, watch such a lecture, because I haven't seen such a lecture in other fields. So it is very interesting for such a great academician to also focus on the teaching part of, training part of the future generations. Thank you for this interesting topic. I say my thank you because it is really interesting, and I want Professor Sevgi to introduce himself.
Okay, thank you, Ömer, and thank you, Ali, for the invitation and for tonight's organization. Our topic is from engineering electromagnetics to electromagnetics engineering. I'm a university professor, and I have been studying in electromagnetics for nearly more than 3 decades, nearly 4 decades. I graduated from one of the top universities in Turkey, from Istanbul Technical University, and then I did my PhD in New York Polytechnic University under the supervision of Professor Leopold Felsen, late Professor Felsen, who was one of the giants in electromagnetics. Then I spent 2 years in Raytheon, Canada division, Raytheon Canada. We studied on high-frequency surface wave radars during the trials and installation of those radars in the Atlantic Ocean for ocean surveillance. Then I spent 1 year with UMass, University of Massachusetts, in Lowell campus. I spent 20 years in Istanbul Technical University as a professor, then spent another 20 years partly in Doğuş University and now in Okan University. The last two are foundation universities in Turkey. So my specialty is, my expertise is electromagnetics. I'm an IEEE fellow. I got this fellowship in 2009. And I am also APS Distinguished Lecturer for the term 2020-2022. So I think this introduction is enough and can start the presentation. So this topic is important in teaching and training next generations, but it is not a new topic. I have studied this topic for nearly 15 years, more than 15 years. This is, I think, the first special issue with the same title in one of Turkish international journals in English, but under TÜBİTAK, was published in 2006. So lately, I have given the same distinguished lecture talk in Istanbul, in Iran, in India, in France, Poland, also in different institutes in India, mostly in India, Australia, and now we are having this talk with you under IEEE Connecting Experts program, which is organized by Region 8 Young Professionals Group. I have also some other topics under this distinguished lecture program. And these are the books I have published with the IEEE Press, Wiley, and also with Artec House. And the other one is guided wave theory, another distinguished lecture topic. I also have one topic for electromagnetic wave propagation modeling and simulation. Next one is diffraction, scattering and diffraction modeling and simulation. Diffraction is a critical phenomenon in electromagnetics. From design to market, EMC engineering, electromagnetic compatibility engineering is another distinguished lecture talk. And finally, antennas and antenna arrays, beamforming and beam steering is another topic. So here is the outline of tonight's, this afternoon's talk. We are going to see a few slides about the definition of engineering. Then we will move to electromagnetic engineering and modeling and simulation in electromagnetics is very critical, is a challenge. So we will see several slides on that part. Since modeling and simulation necessitates software calibration, we will focus on that also. And we will see some electromagnetic virtual tools which can be used in teaching, training young students or researchers in this area. The talk will end with the conclusions and, of course, discussions. So let's see the engineering first. Actually, life is problem solving. So we are, the mathematicians deal with the existence and uniqueness of the solution. So showing that a solution exists and unique is the solution for a mathematician. But we are engineers. We deal with observable solutions for real life problems under specified or required accuracy. Stability and accuracy of the solution is critical for us, for engineers. So we are engineers. We do not seek the best solution, not the cheapest solution, not the fastest solution. Depending on the requirements, the budget, the time, the criticalness of the problem, we engineers, we have to seek the optimum solution. So we don't have best, cheapest, or fastest solutions. We always look for optimum solutions. We are engineers. We deal with physics, but we use mathematics as a tool, and we speed up with computers. So physics means real world. Mathematics is a conceptual word. And once you use computer, that's a synthetic word. So this necessitates an intelligent balance among the theory, practice, and computation, which means mathematical background must be strong. We also need engineering experience. We also need numerical simulation capabilities in electromagnetics engineering. So we are engineers. Engineers always speak with numbers, and a number is meaningful if it is given as a result of only a measurement or a computation. We are not talking about the guess word. So we need to well understand the definitions of critical terms like accuracy, sensitivity, precision, resolution, error. So results are not meaningful if you don't state the uncertainty in your results, which means the error under the confidence limit. Because real life problems are not deterministic. They are not stationary, they are not linear, they are not homogeneous. But especially in teaching, and in most of engineering cases, we assume they are. So they bring uncertainty and error. For example, suppose you repeat a measurement n times and measure x. Then the mean average value x0 will be the addition of all those values divided by the number of measurements. And the standard deviation, which is error, will be given by the second formula. So if you give a number as a result of your computation or measurement, you should try this with this amount of confidence limit. For example, with 95% of confidence limit, the measured computed value is x0 plus and minus delta x, the error term, as shown in this one. So the engineers can only give a limit value between minimum and maximum values. So we can only say that x is between this minimum value and maximum value. Suppose you do test for a vehicle and measure electric fields in volts per meter, for example. So you should answer these fundamental questions. Who will do the tests and measurements? In which environments will the tests and measurements be performed? What type of equipment will be used during the tests and measurements? Who will control, monitor these tests and measurements? Who will control and authorize everything to process, including reporting? So how will you be sure that everything is okay during these processes? How will you control and present systematic and random errors? How will you present the results? So these are the critical questions that any engineer should answer before doing tests or measurements. And the keywords are authorization, accreditation, calibration, and certification. Remember, physics, the real world, is a subset of the conceptual world, mathematics, and they are both subset of the computation, discrete world. So your mathematical solution may or may not correspond to the physical solution. Also, a discrete solution may or may not be your mathematical solution. So it is the engineer's task to seek the physical solution in the discrete environment. So if you do measurements or tests or computation using the discrete computer environment, you have to be very careful. Let me give you an example. For example, in Fourier transform, suppose we have a singleton sine signal, which has f0 as the singleton. So mathematical Fourier transform gives signals at plus and minus f0. So we have negative frequencies in mathematical domain, but in physical domain, we only have positive frequencies. But if you apply discrete Fourier transform or fast Fourier transform, that introduce periodicity both in time and frequency. So you have infinite number of tones, infinite number of frequencies in discrete environment. And if the frequency you deal with is beyond the maximum frequency, you may have ghost or uncaptured frequency signals. So fast Fourier transform also gives signals at negative frequencies. Here are the DFT and FFT challenges: discretization, numerical integration, and finite time duration. In mathematical world, the mathematical definition of Fourier transform is not a problem, but discrete Fourier transform definitions are critical. So you should be aware of these two equations. The frequency resolution depends on capital T, which is the record time of your signal in the time, and maximum frequency depends on the sampling rate, delta T. Let me show you all of these in this slide. Suppose you have 4 tones, F1, F2, F3, and F4, and you do sampling and recording time so that your frequency domain is between maximum minus Fmax and plus Fmax, and F1, F2, F3, and F4 appear as shown on this slide. So if you don't pay attention to discretization requirements, then only F1 will appear within this band. The others will be ghost signals. F2, F3, and F4 disappears, and they appear as ghost signals at these places. So we have to be very careful when you deal with discrete environment. These are all ghost signals. So physics, mathematics, and discrete environment, their interrelations are critical for all engineers. Okay, let's move on electromagnetic engineering and see a few slides on this topic. So the role of electromagnetic fields in our lives has been increasing. We have been surrounded by electromagnetic waves everywhere. We have communication systems, remote sensing, integrated command control, surveillance systems, intelligent transportation systems, fast trains, medicine, education, marketing, defense. They are all different areas where electromagnetic fields are critical. We have systems with frequencies from DC to terahertz and more, and the sizes of those systems may vary from nanometers to kilometers wide. And almost all of these systems are broadband and digital today, and they have to operate close to each other. That results in severe electromagnetic interference problems. So EMC engineering is also critical. So we therefore have witnessed the transformation from engineering electromagnetics to electromagnetic engineering for the last few decades. So instead of calling microwave engineering, biomedical engineering, antenna, propagation, communication engineering, we prefer to name it as electromagnetic engineering. And these are subtitles, critical research and teaching areas under electromagnetic engineering. We have radio wave propagation here, microwave circuits, integrated surveillance systems, biomedical engineering, subsurface tomography, remote sensing, new materials, 4G, 5G wireless systems, EMC, EMI, antenna, RCS analysis and diffraction, radars, energy supply, motors and generators. So there are different critical research and teaching areas under electromagnetic engineering. We are lucky because we have well-established theory. Electromagnetic theory is well-established with Maxwell's equation. Here you see Maxwell's equation on the left in differential form, on the right in integral form. So differential means subtraction, integral means addition. So electromagnetic engineers use two different theories. One is electromagnetic theory, the other one is circuit theory. But in fact, circuit theory is a subset of electromagnetic theory. So every equation under circuit theory can be derived from electromagnetic theory. So actually, we have only electromagnetic theory. New generations may find these equations unattractive, but all we need is to differentiate, subtract, and integrate at electric field and magnetic field in time and space. So we have Maxwell's equations, which are general, the solution of every problems from antenna engineering to diffraction, biomedical. But once you state your boundary condition, the solution is yours. The problem is yours and the solution is yours. So usually we define problems by given the Maxwell's equations plus boundary conditions and initial value conditions, of course. If we are lucky, we have analytical exact solution, mathematical exact solutions, but unfortunately, they appear only for a limited number of highly idealized problems. In addition, they are usually in the form of integral or infinite series summation. So their numerical computation is also a challenge. Usually, we have analytical approximate solutions, and we call them high-frequency asymptotics. Lately, in the last couple of decades, we have numerical solutions, but they suffer discretization, memory, and time requirements may be critical also. Under electromagnetic theory, all of the problems can be divided into three, roughly speaking. The first part is antenna and radiation problems. So you use Maxwell's equations plus boundary conditions. You define and use auxiliary scalar and vector potential functions to then end up with electric and magnetic fields. So if you deal with antenna and radiation problems, using potential functions may mostly are easier to deal with. The second group is radar cross-section and scattering problems, including diffraction. So again, we start with Maxwell's equations and the boundary conditions. We represent total fields in terms of incident and scattered fields. We send an incident field onto the object. This means we know the incident field, satisfy the boundary conditions, and then calculate the scattered field. So the addition of incident and scattered field will give us total fields. The last group is guided wave propagation problems. They're quite different, but we start with Maxwell's equations plus boundary conditions first. We apply transverse and longitudinal decomposition, and then we deal with either eigenvalue problem, source-free solutions, or Green's function problems, source-driven problems. And here are the discrete observables that we use in numerical computations or measurements. We may have rays, we have geometric optic rays, physical optic rays, geometric theory of diffraction, uniform theory of diffraction, physical theory of diffraction. We also have modes or trapped guided regions. We may have normal modes, adiabatic modes, or intrinsic modes. We can use beams as complex source points, pulse beams, or parabolic equation. And we can use them in hybrid form. For example, ray plus mode, or mode plus parabolic equation, or ray plus parabolic equation. And because of the high-speed computers in our lives, lately we can directly deal with time domain objects like wavefronts, wave packets, and potentials. So here, observable means computable or measurable. High-frequency asymptotics can be divided into two: geometric optics, GTD and UTD. They are ray-based models, but physical optics and PTD are current-induced mode-based solutions. And here are well-known numerical techniques: FDDT, TLM in the time domain, method of moments, parabolic equation, and finite element in the frequency domain. But we can also use method of moments and finite element in the time domain directly. They are quite difficult, but doable. So when you face an electromagnetic engineering problem, you should consider the frequency range, signal strength, time and its duration, its continuities, impedance, and boundary conditions, of course. And among these, you should take into account time frequency, frequency geometry, and frequency impedance relations. Now, let's move on to the third part, modeling and simulation in electromagnetics. So we deal mostly with deterministic problems, and we use root search, n by n systems of equations. We do numerical integrations such as radiation integrals. We do differentiation such as in wave equations, and then we interpolate and extrapolate results. Life is stochastic, so randomness, probabilistic, statistics, error and uncertainty, and confidence levels are also important in this area. So we have different modeling and simulation problems. We may have task trainer simulation, virtual reality, mannequin-based simulations, live simulations. Also, we have physics-based simulations. Here, we are going to talk about physics-based simulation. This is the problem we deal with in this presentation. And we mean computer numerical simulations based on physical understanding in mathematical representation of a real problem, real-life problem, device, or system. So when we define a model, it is a physical or mathematical abstraction of a real-world process, device, or concept. Simulation concerns with modeling of real-world problems. Numerical simulation refers to use of computation, and a simulator is a program or a series of programs. And why and when do we need simulations? Usually, it is expensive and time-consuming to do tests with real systems. Sometimes it is dangerous to do tests with real systems. Very often, it's impossible to do tests with real systems, and sometimes the real system has not appeared yet. That's why we do simulation, modeling and simulation. And at the end, if we have a simulator, the best part is we can play what-if type games. So we have a real-world problem, we have a mathematical model, we have a computer program, and the result is displayed on the screen. And on the right, we can use numerical analysis and parameter optimization. And on the left, we can add some computer graphics and visualization capabilities, and we can design graphical user interface. And all of these is called electromagnetic package or electromagnetic virtual tool. And we start with Maxwell's equations, we do discretization, and we end up with our virtual tool. And depending on the problem, we have two types of representations: closed form, matrix representations, and open form representation. In closed form, you have n number of unknowns and n number of independent equations. So it is stable, but huge matrices are problems. If the construction is also another problem. An example for closed form representation is method of moments. In open form, they are conditionally stable. The small size, a few line codes are enough, maybe enough, and they are easy to construct. So example is FDDT, finite difference time domain method. So we have a software, and we need to calibrate that software. So when you build a model, you introduce assumptions, you neglect several effects, you do approximations, justifications, and at the end you do discretization. So the first four belong to analog world, last one belongs to synthetic world. So you are in a real danger. So you need validation, verification, and calibration, VV&C. So validation asks the question whether the right model is built. Verification, on the other hand, asks the question whether the model you choose is built right. Calibration is nothing but comparing the test's results against reference data. But what is reference? That's the critical question. Very often we do not have reference. We have to assume something as a reference. So analytical exact solutions may be used as reference. Mathematically, if we know the exact solutions, they are perfect for reference. For example, flat Earth and two-ray model is used to calibrate open field test sites and also anechoic chambers. And half wavelength dipole and horn antennas, since we know their mathematical exact solutions, they are used in antenna calibration. And this is the chart between or among real-world problem, conceptual model, and a computer model. So you start with the real-world problem, then you end up with one of the mathematical models, and you do conceptual validity. You do this with physics-based analytical modeling. Then, once you are sure that this mathematical model represents or may represent real-world problems, you write your computer model, and you do code verification using computer programming. At the end, you run your simulator computer and get a result. And you need to test your result against the real data, and you do this with operational validity through numerical and physical experimentation. And among all these, you need to well understand the data analysis and signal processing techniques. So we have analytical based models and numerical based models. And here is the definition of analytical and numerical based models. In analytical based model, you start with the boundary conditions and you write, or you end up with the analytical model. You develop your analytical model, and then you go to computer, user's data is supplied, and numerical results is obtained. So you solve your problem, computer only gives you a result. When it comes to numerical model, you develop your model at the beginning without the boundary conditions. So anybody can introduce his or her geometry and get the numerical results. Actually, you discretize your problem, computer solves it for you. More precisely, you make the computer solve the problem for you. Here is an analytical model-based approach. This is an antenna array program. We have published different tutorials in the IEEE Antenna Propagation magazine and share different virtual tools. This is one of them. And you can use linear, planar, or circular arrays of isotropic radiators and then observe the radiation characteristics, beamforming, and beam steering capabilities. So this is an analytical model-based approach, because behind this virtual tool, we have only one equation, this one. And this is the equations and figure. So you locate number of radiators, you choose your observation point with this rectangular coordinate system, and using this one, you get this beamforming and beam steering capabilities. So there is only one mathematical equation. The rest is visualization and graphical user interface design. Another example is two-dimensional propagation. So suppose you have height, vertical, and horizontal dimensions. You have buildings. You put your transmit antenna here. You locate receiver antenna here, and you search for different type of rays. The first one is direct ray. The second one is reflected ray, and the third one is tip diffracted or edge diffracted rays. So you search all of the rays and then add them up and get the electric fields at this point. So you can change the location of points where there is no direct ray, but only diffracted waves and secondary reflections contribute. Still, you can find each individual rays, either direct, reflected, or diffracted, and then sum up them and get the results. So this is another analytical model-based approach. Everything is done by yourself with mathematical equations. But if you use this one, ray shooting, for this scenario, for example, there is a transmit antenna, and you shoot the rays, and then you trace the rays, whether they reach the receiver or not. This is a ray shooting algorithm. This is a numerical model-based approach because the only equation you use is geometric optic ray summation. It's an analytical-based model. You calculate the contributions of each eigenrays. Eigenray means rays from transmitter, emanating from transmitter reaching to the receiver. But in the second one, geometric optic ray shooting is a numerical-based model. You discretize the medium and shoot the ray. Ray paths are plotted by the program. So it is critical whether your model is analytical or numerical. This is another example, also numerical-based model. So you have ray paths, you have transmitter here, and you have ray paths, and this is a atmospheric refractivity variations, which represent humidity, temperature, and pressure of the atmosphere. And under these conditions, ray paths are curves, as you see here. Another example, if you change the refractivity path, then you get different ray paths. So this is a ray shooting numerical-based model. Another example is for the numerical-based model, parabolic equation. So we have two-dimensional Helmholtz wave equation, and z is the height, x is the range, and you do this approximation, and then reduce the Helmholtz wave equation into parabolic form, and get this one. So you have only second derivative with respect to height, but only first derivative with respect to range. So it is a parabolic equation form, and that is very suitable to deal with fast Fourier transform. So that's a two-way problem, and the other one is one-way problem. What we do in Fourier-based parabolic equation method, so you have an initial antenna profile, as you see here, and step by step you move and progress the solution by this equation. So this is the only equation which can give you any field profile under any circumstances, atmospheric, homogeneous atmosphere, and non-flat terrain models. So you supply me the initial field profile here, and then I apply this equation, which means I get the Fourier transform, FFT, do a complex multiplication, do inverse FFT, another simple multiplication. I get the result on the next vertical platform. So I get this one for the new initial profile and repeat it, and step by step I progress the waves from left to the right. So here you see an example. Everything is done with that simple one equation, where you use Fourier transform FFT and inverse FFT. Another one, for example, it shows you the field propagation through inhomogeneous atmosphere over non-flat terrain profile. So these are all virtual tools that we have published their tutorials in the Antennas and Propagation magazine and share their virtual tools. So SSPE propagation parabolic equation can also be used two-way, forward and backward, and then backward propagated waves, even trapped waves, can be modeled, as shown on these videos. This is another example, but this is time domain propagation by using two-dimensional FTDT model. So you can put number of points, create non-flat terrain profile, and then observe wave propagation. The beauty is that you can record these videos and show your students or your colleagues. So visualization is the power and beauty of all these virtual tools. So this problem belongs to analytical reference model because we know the mathematical solution. So this is a two-dimensional wave equation, which is called Avery equation. If the n squared is like this, and then the solution is given in terms of AD functions. So soft boundary condition means transverse electric, hard boundary condition means transverse magnetic conditions. And since you have this summation in terms of AD functions, you can use this as the reference data to calibrate your numerical models. So this is an area function. If x is negative, then it looks like a sine or cosine waves, standing waves. When x is positive, it's an exponentially decaying evanescent waves. So area function may represent both standing waves and also evanescent waves. These are the modes, analytical solutions, and you add those modes and get different results, mode profiles, build different solutions. So here, this is the Gauss type source, and you use different number of modes, and that one is the area function solution, and then you represent the source exactly, and then get the fields at different ranges. So mode summation is nothing but Fourier series representation of any given source function. So this is another example, and you can use realistic sources, beam sources, radiation patterns, even upward or downward tilted. But if the tilt angle is 0, only, for example, less than 20 modes may be enough. But if you increase the tilt angle, the number of required modes, the area functions, drastically increases. So you have to be very careful when calculating analytical reference solutions. So numerical computation of an exact reference solution may be a challenge. Now here, analytical versus parabolic equation. We have two beam type solutions, upward tilted, downward tilted, and their interference gives you this picture in two-dimensional range, height space, and you get exactly the same result with the numerical simulator. So these are height variations of fields at different ranges, and the match is clearly observed in these pictures among analytical, parabolic equation, and finite element models. Another simple problem is packed flat earth and single knife edge. So if you have a single knife edge between the transmitter and receiver, you can use 4 rays: the direct one, ground reflected, tip diffracted. So wherever you put the receiver, only 4 possible either rays are enough. So this is analytical approximate solution, but quite accurate, that can also be used as reference. So here, on top, parabolic equation, here 4-ray analytical model, and as you see, again, almost very good agreement is observed in this 3-dimensional plot here with different boundary conditions. And this is the one of recent books about radio wave propagation and parabolic equation modeling. The authors are myself and my colleague, Professor Gökhan Apaydın. Now, how we use these virtual tools in teaching and training? Let me show you a few slides, and then we will end up the conclusions. So we have developed and introduced multi-purpose virtual tools that can be used in most of the classical electromagnetic lectures, as well as in novel engineering programs. We have always looked for something which would be useful, give physical insights, and effective, so that the young researchers and students can use them intelligently. Note, those virtual tools should be simple to use. The user should be able to change some parameters, but we have to fix some of them so the inexperienced user will not get lost. And also, it should be open to non-physical results to some extent, so that the user may comment on them, may ask questions and try to answer why the solution agrees, why not agrees, etc. So this is a generic one-slide front panel of our virtual tools. Usually we have geometry block, boundary conditions block. We define source here. We get the outputs, graphics here. The simulation videos can be captured in this window. And we have run or plot or exit commands. So this is a generic front panel, and these are several of them: propagation, antenna, scattering, guided wave theory. So they can be used in scattering and diffraction courses, either undergraduate level or graduate level. They can be used in guided wave problems in both levels, and also antenna and radiation problems. These are all virtual tools that are used. This is one of them. This is one of the most sophisticated one, which is in three-dimensional. It predicts RCS of realistic targets using both method of moments and finite difference time domain. You only need to supply a real target and its graphics files. So once you have these graphics files, the virtual tool develops its discrete files for FDDT and for method of moments NEC calculations. And then you can capture these type of realistic videos. So you have a plane wave coming here, pulse in time, and transient scattering around the object. So you report these transient effects within only a few nanoseconds, perhaps, and then you do FFT and get the frequency domain results in terms of RCS versus frequency or RCS versus angle. So these are other targets. So you have here two targets, F-16 aircrafts. You have one F-16 here. So if you have that virtual tool, you can run it, get the FDDT results, run FFT, and get the frequency domain results, and then plot the results as shown on this slide. So as I said before, you can easily play what-if type games if you have that virtual tool, if you are experienced enough. For example, what if instead of one single F-16, I have two F-16 flying one on top of the other or side by side? What if their RCS contributions? Can easily get the results. As an example, so you have RCS in dB versus frequency. The red one, the red curve belongs to one F-16, this one, and the blue dashed curve belongs to two F-16 targets side by side. So as you see, RCS at, for example, this frequency of two targets is less than single target, but at this frequency more than the single target. Again, less, more, less, more. So it is not easy to predict RCS of any object, either simple or complicated, from, for example, low frequency values to high frequency values. So you have to compute or you have to measure at every single frequency. So scattering effects. So scattering is the definition which includes reflection, refraction, and diffraction. Sharp edges and tips cause diffraction, and source-induced currents can be divided into two. And we have physical theory of diffraction or fringe waves in diffraction theory. So this is a short video showing the total fields of a two-dimensional text strip with scattered fields from different incident angle, total fields again, and scattered only fields. So you can easily record these videos and train your students or your colleagues. So these are other videos on the left, total fields, on the right, only scattered fields. So if you subtract the incident field from this, you get the scattered only fields. For different aspects and angles. So the details of every scattering phenomenon, diffraction phenomenon, can clearly be observed and discussed with these simulators. This is a tool that we developed lately, diffraction of a wedge problem. We have pulsed, so you see how reflections and diffractions occur. And then you do the Fourier transform by using FFT and get the total fields along the object for TE-type problem, source boundary condition, and half boundary conditions. And then total fields and diffracted fields for different wedge angles, for different angle of illumination. So huge amount of results. And this is the last book that is on the market nowadays, within a day or two, about diffraction modeling and simulation. Now the conclusions. So wave-oriented electromagnetic engineering is an effective way of identifying both technical and educational challenges in a rapidly changing, internet-driven, globalized world. The computer capabilities has revolutionized the analysis of complex systems. Therefore, modeling and simulation and validation, verification, and calibration has become crucial. You should well understand physics behind mathematics before using simulations and compare numerical results with experiments. You have to keep in mind the assumptions and validity ranges of the mathematical model you are using. So you should look at the object as a whole, but also pay attention to every details in terms of different electromagnetic phenomena, scattering, diffraction, fringe waves, etc. And lastly, multiphysics has become essential, so establish interdisciplinary collaboration. So we need to use, for example, electrodynamics together with thermodynamics. So multiphysics has become essential. So although novel approaches such as virtual reality or artificial intelligence are very attractive, hands-on training is a must in electromagnetic engineering, and basic lectures such as measurement techniques should be renewed accordingly. So teaching training via these virtual tools is highly effective. Students first play with these tools, visualize electromagnetic wave-object interaction, reproduce the results of the given scenario, play with the virtual tools, and then create their own scenarios. They can then start electromagnetic theory and play with Maxwell equations. So this establishes understanding physics, mathematics relation. So students who are further interested in electromagnetics, then they can get the supplied source codes and modify, develop better ones. Today's engineering students are very lucky because there are excellent commercial packages and measurement devices. But also today's engineering students are very unlucky because there are excellent commercial packages and measurement devices. So depending on your aspect angle, you may be very lucky or very unlucky. So this is the motto I used in my first book, let's do it. And the second one, yes, you can. And this is the IEEE motto. Tell me, I'll forget. Show me, I'll remember. Involve me, I'll understand. And that's the end of my presentation. Thank you. I hope you enjoy it.
Thank you very much, Professor Sevgi, for this great lecture. First, I'm looking for the question from the attendees. Dear attendees, if you have a question, please feel free to ask. All right.
You can also send me your questions via emails if you are really interested in these virtual tools and electromagnetic packages.
Of course. I have a question, but first let me write your email. Elas Levent Sevgi. That's not as I remember. Okay.
Also write down the second one, levent.sevgi@okan.edu.tr.
Okay, Professor, if you want, then you can write. I have a question. You talk about some simulation techniques to understand to teach the electromagnetics, but I wonder I don't know, I am not so familiar, but in electromagnetics there is another field, computation electromagnetics, something like that. And here people deal with some people use some numerical methods. I just wonder, as a guy who is unfamiliar to electromagnetics, do you have any special training to teach the students to study the computation electromagnetics? For example, if you in some fields you may need to teach some software skills. You may need some software skills to. But in some disciplines, some sub-disciplines, you may not need something like that. But I just wonder, for example, if you talk about communication, the classical communication theory students don't need so much software skills except the MATLAB. But if you are a network engineer, computer network engineer, then you need to use different tools and maybe some other programming language, C, C++, Python, something like that. So I just wonder what is the difference to teach a computation electromagnetics student from the classical electromagnetics student?
We use all the models, all the numerical techniques, and also analytical techniques that are taught under computational electromagnetics course. But we do this from the most simplest case to the most comprehensive ones. For example, for the undergraduate students, you can teach only, for example, a single radiator or two radiators, two isotropic radiators, and show the students how electronic beam forms and beam steers. Or you can use, even high school students can use Snell's law, and geometric optic ray reflection and diffraction can be taught. So you start from the very simple case for the undergraduate lectures, using MATLAB, of course. Most of them are in MATLAB. And then in the graduate level or PhD level courses, you end up with computational techniques. So you may go into details of, for example, method of moments in a graduate level course, or finite difference time domain method in graduate level course, or finite element methods. But here first, you teach students how to define a physical problem, how to use mathematical representation, some equations, and then how to use, with or without MATLAB, computers. So that's quite different. For example, we have excellent antenna, commercial antenna packages. You do not need to be an engineer or antenna engineer to design an antenna system, for example, because you have excellent commercial packages. But it's only a game if you don't know the physics behind those commercial packages, then you may be in trouble. So we should remember that we have to teach first theory physics, then theory mathematics, and then we use computers. And we have to intelligently establish a balance among them. So that's the difference. The philosophy is different in teaching without tools than teaching graduate level or undergraduate level of computational electromagnetics.
Thank you very much, Professor Sevgi. Is there any question from the attendees? Okay. If you have another question later this webinar, you may send him an email. You may drop an email to Professor Sevgi. And Professor Sevgi, thank you very much for this valuable lecture. And
how many attendees are there, Ömer?
As I see, 5 on the Zoom, but it is 7 at this point, and also from the YouTube site we had 4, and also Facebook site. Totally, it seems about 15.
Yes.
It varies between 15, 12, something like that. Because we launch our webinar via 3 platforms: Facebook, YouTube, and Zoom. Here in Zoom, we host the IEEE members, but from the other one,
Anybody can attend.
yeah. Thank you very much for your participation, and it seems there is no more question. Thank you very much, Professor Sevgi, for this great webinar, this great lecture, distinguished lecture. And I would like to say we will continue our community expert webinars 5 days later. So stay tuned. So keep in touch. Bye for this. Bye for now. Okay. Thank you very much.
Bye-bye.
Just they post a question, but when the doctor is leaving.